All right. Hello, everyone. Now, for the next talk, we'll have Martin Bidlingmaier, who's about to finish his PhD at Aarhus University on the multiverse models. Go ahead.
Yeah, thank you. So I'm going to talk about multiverse models for dependent type theory. So, yes. So what do you mean by multiverse here? What do I mean by universe here? First of all, I don't really mean it's only barely related to the type theoretic, like the type, universe type. What I mean by universe here is simply a mathematical universe. So a model of the mathematics we're doing, the model of dependent type theory. And then a universe model, the usual universe models, are the categorical ones for type theory, are given by LCC, so locally Cartesian closed categories. And then if you have, like, for the bare minimal dependent type theory, and then with additional structure for more complicated type theories. So that's what I would call a universe model. And then the multiverse model is given by taking the collection or category of all of these small universe models itself as a model. Yeah, so I think this is an interesting point of view in itself, interesting. But I also think that there's some problems that can be attacked in very new ways if you have this multiverse approach. So okay, so how does this even barely make sense to just take the collection of all these universes? So one motivation is this proposition, this informal proposition here. So if you take some kind of dependent type theory, whatever you understand by a dependent type theory, then you have a type in the empty context, sigma, and then you form the extension of this type theory where you add a new constant symbol in the empty context of type sigma. Then I hope you can show that there's a bijection between the types in the base type theory, but where you work in the context which has a variable of type sigma, and the set of types in the extended type theory, but in the empty context. That's I think what the context extension is supposed to represent. And of course, there is something similar for terms. So the way I interpret this is that the contexts in type theory somehow parameterize extensions of the base type theory that you're working with, right? So the context V in sigma, for example, represents this extension T prime that we're talking about here. So the universe models, those are due to Seeley, I think. Seeley proved that dependent type theories somehow correspond to LCC categories. But then, according to this proposition, the contexts somehow correspond to type theories themselves. So if we take the transitivity here, then we should somehow have that contexts correspond to LCC categories. So every context should be somehow some LCC category. So that is one way to see this. So in the multiverse model, we have all those different categories available. A different one is this table here, which kind of shows that the universe models due to Seeley are really just small parts or submodels of the multiverse model. So if we just look at the first line here, which shows how you interpret contexts. So according to Seeley, in a single universe model with a fixed C, this is simply an object of the category C. Tautologically equivalent, this is to just saying that the context is a slice category over C, because, well, what is a slice category over C? It's, well, given by an object gamma, and then the category given by slicing. And then the last column is always obtained by just removing the reference to C from this. So here we have a slice category over C, and then if we want to not talk about C, we simply say it's an arbitrary LCC category. Then in the next line we have to define the morphisms or the substitutions, how we want to interpret those. And then in the universe models, it's pretty obvious that it's simply a morphism in the same direction. Equivalently, if we want to phrase all of this in terms of slice categories, we can just take the pullback functor for that morphism F. And then we get an LCC functor in the opposite direction of slice categories. And in fact, every LCC functor of slice categories which commutes with like the pullback functor from C to C over gamma and C over delta is automatically isomorphic to some kind of pullback functor. So in a sense, we don't even have to talk about F. We can just say it's an LCC functor of the slice categories over C. And then again, if we remove reference to C, we simply say, well, it's an LCC functor. Then in the third line, we define what the types are supposed to represent. In Seeley's model, this is a morphism into gamma with arbitrary domain. That is by definition simply an object of the slice category. And then forgetting that this is a slice category, we simply say it's an object in the LCC category in the multiverse model. And then fourth, the terms are given by according to Seeley by the sections to the morphism representing the type. And such a section can equivalently be described as a morphism from the identity morphism on gamma to sigma in the slice category. So if you write down what it means to be a section, that's basically what it means for S to be a morphism in the slice category. And then we notice that the identity on gamma is the terminal object in the slice category. So if we want to generalize this to an arbitrary LCC category, we simply say that it's a morphism from the terminal object to whatever type we're talking about. Then substitution, according to Seeley, is given by forming such a pullback square and then taking this left projection. Then if we have already, if we just have the pullback functor available already, we don't even have to make a choice here of pullback. We simply apply the pullback functor. And then if we don't know anymore that that this is really a pullback functor, we simply apply the functor again. Context extensions are given in Seeley's universe models by taking the domain of this type. In terms of slice categories, we can form an iterated slice, which is really, again, just a normal slice or isomorphic to one. And then in the multiverse model, by this analogy, we take the slice category again. And then sigma and pi types are interpreted using more structure of the of LCC categories. Yeah, so if nothing else, then I hope that like the first 4 or 5 lines of this table are really what you would take away from this talk, I think. Okay, so even Seeley's original interpretation suffered from coherence problems. So a mismatch where on the one hand side you want equality and on the other you only have isomorphism. And we also have problems, although slightly different problems with the multiverse model. So the first thing is that substitution in type theory should commute up to equality with type formers. So that means that if I substitute an equality type, which here I simply denote by application because that's how substitution is defined in the multiverse model, then you want an equality. Then you want to be able to compute this as simply taking the equality type of the substitutions. But an LCC functor preserves structure up to isomorphism, or generally like something functors in category theory usually only preserve these things up to isomorphism because that's much more natural. And that's also the case here. Like we have an isomorphism, but type theory really wants an equality here. And then, so there's a version of the multiverse model for 1 categories corresponding to extensional dependent type theory, and then kind of a version of it with infinity categories for intensional type theory. Basically, whenever you say category, you just say infinity category instead, and then you have to be a little careful, but essentially it's kind of the same thing. But for infinity categories, you have this new problem where you also have to care about substitutions of terms. So in 1 categories that goes away because these morphisms are usually such that uniquely determined such that some diagram commutes, and that this uniqueness implies that they're once you have solved the first issue, the second issue goes away because some diagram still commutes, and so the morphism must be the same one. But for infinity categories, you can only conclude that there is some canonic or contractible homotopy, and so you also have to take care of this. And then the third issue is that the slide, so remember that the context extension in the multiverse model is, we want to interpret this as taking slice categories. But so the axioms of type theory, or the axioms of categories with families, for example, they demand that this has a one categorical universal property. And these slice categories only have this, they have the same universal property, but in a higher sense. So this diagram here, this commutes up to some kind of canonical equivalence or isomorphism. And then also the factorization that needs to exist. So this map here only exists up to contractible isomorphism or equivalence. So those are the problems that we have to explain somehow, or how we can avoid them. Yeah, so the thing about these things is always that that type theory is really a one categorical thing. Like the CWF structure is something that a one category has, but we're trying to interpret this as some kind of in some kind of higher category. Even in the universe model, basically that's the problem. So even one categorically, the category of all categories is a two category, or the category of all LCC categories is naturally a two category. So that's really the mismatch that's going on here. And I would argue that model category theory, in the sense of model categories as in homotopy theory, Quillen, that's the name, are the tool that are a good tool for attacking this thing, because model categories are precisely about presenting some kind of higher category as a one category with some structure. And so you can hope that, so the general idea is that we want to find a higher equivalence. So in this case, a Quillen equivalence of the category of all locally Cartesian closed categories, locally Cartesian closed categories, LCC, with some kind of M, such that M is one categorically better behaved. So as one categories, they shouldn't be isomorphic or equivalent, but the higher categories they represent should still be the same ones, so that you can say that you haven't meaningfully changed the semantics. And so what we're going to look at here is like a succession of three model categories, each in a version for one categories and infinity categories. So first, the model category of sketches, then a model category of strict LCC categories, or strict LCC infinity categories. And that already solves like the first two issues that we had with the substitution of type and term formers. And then third, this model category of algebraically cofibrant strict LCC categories. And for one categories that solves the third issue, but for infinity categories that breaks something, and then so you so you can only prove a weaker result there. Yeah. Okay, so what are sketches? So this is again constructed in 3 steps. So first, you want to start choose some kind of base model category C. So if you want to do one categories, then you choose cat with the natural canonical model structure on it. And for infinity categories, you want to use either simplicial sets with the Joyal model structure, or better yet, marked simplicial sets. So those are better because they're simplically enriched. So the model category is enriched as a model category for simplicial sets, for marked simplicial sets. Then second, you define a set of shape objects of markings. So these objects should represent the shape of the universal objects that you want to talk about. So in our case, LCC categories are finitely complete. So they have a terminal object, which is this category here represented by a single object, this dot, that's not a stain on your screen. Then second, by a square, so a pullback square, which is this one. And then third, the dependent product. So that this is supposed to be the dependent product of G along F, and then this epsilon is the evaluation maps. So these are just these finite discrete objects, either represented as categories or as simplicial sets. And then once you've fixed these shapes, you form the model category of marked objects, which is due to USF. So a marked object consists of an object in the base category in which you've distinguished a set of maps from K to X, where K is one of those shapes. So for example, here we would have a category where some objects are marked as terminal, some squares are marked as pullback squares, and some diagrams of this shape are marked as dependent products and their evaluation maps. And this carries a model structure. And then third, you want to localize this model structure, like the left Gauss field localization, so that you reduce the fibrant objects to those marked objects where the marked things are actually what they're supposed to be. So a square is marked if and only if it is a pullback square, and all pullback squares exist. An object is marked as terminal object if and only if it is a terminal object, and a terminal object exists, and so forth. So that's how you obtain this model category of sketches. And it's a pretty general mechanism, and you can probably adapt this to other universal objects. So the second step uses algebraically fibrant objects. So that's, again, a pretty general mechanism. So here you have a model category M, you fix a set of trivial cofibrations, and then you want to look at objects which are equipped with lifts against the trivial cofibrations in J. So usually the fibrant objects are such that such lift exists, but here we want to make it part of the structure, and then morphisms are supposed to preserve these lifts up to equality. Usually they're only preserved up to homotopy. And then you can show this maybe surprising result that this category of algebraically fibrant objects carries model structure, which is Quillen equivalent to the original one. So this is a category that is one categorically different, but presents the same higher category. And then for higher categories, you probably want to use like an enriched lifting operation, but that's a detail. So we instantiate this for on the sketches to obtain categories of strict LCC categories. So the existence of universal objects like pullbacks is in sketches is encoded, or in the fibrant objects of sketches is encoded via a right lifting property. And so if you fix lifts against those, you fixed a choice of universal object. So you have a canonical pullback square and so on. So you can talk about this. And such choices will be preserved up to equality, which is what we want for type theory, right? Which is why you can show this thing here. So one category, basically one categorically and infinity categorical is very similar here. This category carries CWF structure, supporting extensional equality types and finite product types in one categorical case. And in the infinity categorical case, you have identity types and finite product types, but only weakly so. So weakly meaning that, for example, the computation rules that you're used to, they only hold up to some kind of specified term constructor. So the things are substitution stable up to equality, but the computation rules, those only hold up to some kind of term of the identity type. So why didn't I talk about sigma and pi types here? That's because there is a problem, namely that we want to. So what we want to use is use the structure that the pi functors and sigma functors, the right and left adjoints to pullbacks, to interpret these. But so context extension in SLCC is given by this formal one categorical pushout on the left. So we glue to gamma some morphism with terminal domain along the codomain. So X corresponds to this type sigma that we want to extend gamma with. And we want to glue this morphism to it. And we have to form this one categorical pushout because that's how type theory works. But the size category is only like this homotopy pushout here. So it's not even the one categorical pushout, and it's also in LCC and like in sketches, not on strict categories. And so we have to explain how we can somehow compare this context extension to the size category. And well, if you know something about homotopy pushouts, then you know that there are conditions on when this one categorical pushout is a homotopy pushout. And one sufficient condition is that gamma is cofibrant as an object of this model category SLCC. And indeed, if gamma is cofibrant, then you can construct this equivalence. And using this equivalence, you can interpret pi types and also sigma types. Like if you have a type tau depending on a variable of type sigma, then you first transport this to the size category using the equivalence, and then you apply the pi functor. The problem is that this depends on a choice of equivalence here again. So this wouldn't be substitution stable. So what you need to make sure that it is substitution stable is somehow get this equivalence substitution stable. And this can be done by making gamma is cofibrant into structure again. Which leads us to this next thing, kind of the dual construction, although it's not strictly a dual because model categories, combinatorial model categories are not are not self-dual, but it kind of looks like it. So here you say that an object is algebraically cofibrant if it is a co-algebra for a cofibrant replacement, and this should be co-monad here. So the algebraically fibrant objects can also be phrased like this, where you just say it's an algebra for a fibrant replacement monad. And the intuition is, and I suspect that you can make this formal somehow, is that in our case, that every non-strict LCC functor from some strict category gamma to a strict category delta has a canonical strictification, which it is isomorphic to. And then you can again, surprisingly, show that the category of these co-algebras carries model structure, and which is equivalent to the original model structure. And then we just apply this machinery to SLCC, and one categorically that solves our problems. So there we get a full model of extensional dependent type theory as we want. Infinity categorical, there's a very subtle thing going on where so the problem there is that this category is not closed under context extensions in SLCC, which is not something that you would expect by default, but it happens to be true in the one categorical case. Yeah, and it is a very technical thing, but yeah, which I can't go into detail here, but yeah. Right, so I have a few open problems that I think are interesting to look at. Like first, this issue with the context extensions for the infinity categorical case, obviously. I kind of suspect that it's really like a hack or a happy coincidence that it works for one categories. So I suspect that this third step with the co-algebras, that you have to use some very different mechanism here, but it could also be that you can adapt it somehow. I just don't know how. So the second thing is that these multiverse models should allow us to talk about type classifiers, which are, I think, which I call them that because it's similar to the object classifiers in topos theory. So the idea is that you want to be able to extend your context by a type variable. So you want to say that there is a new type in this context, and you can substitute it for whatever concrete type that you have in some other context. So in this sense, it's like joining a new object to a topos or the object classifier. And because this thing would not be classified by a type itself, like a universe type, it would avoid Girard's paradox, despite not putting some kind of size restriction on the type variable. And you can probably say something about parametricity, because that thing also has a higher universal property, which is not interesting for context extensions, like the normal ones, but it is like meaningful for extensions by a type. So basically you want to say something about the case where you substitute isomorphic types for the type variable. In one categorically, basically for the same reason, the coherence construction fails for the infinity categorical case. This thing exists in SLCC, but the co-algebras are not closed under arbitrary extensions, under this kind of context extension. But without pi types, there is this construction which can be found in this book, categories, allegories, talk categories, which kind of gets around this issue in a very different way, but without pi types. So you can basically finitely complete categories with sigma types. And then the third one is just generally use model category theory to talk about these coherence construction, because it seems like such an obvious tool to attack these things, but I haven't seen much about this. Like, for example, there's this work on a constructive simplicial set model structure, and the cofibrant replacement looks suspiciously like a cofibrant replacement in categories of algebraically cofibrant objects. So I suspect that you can say that this is somehow this means semi-simplicial, marked semi-simplicial set. So I suspect that that can say something like this. And then the last thing that I want to mention is, which I also have looked at a bit but couldn't solve, is solve basically this question: can you form the model category of strict finitely complete categories where you have associative pullback along both directions, which maybe works, but maybe that doesn't work. And model category theory at least provides a good language to talk about these problems, because it can ask whether this is a Quillen equivalence, and it should be right Quillen equivalence here. Yeah, and right about time. So there's another slide on references, which you can look up, I guess, in the slides. Thank you.
Okay, thanks. Let's silently thank the speaker again.